We'd like to welcome you to the third module of the internal curing series, and this module is dealing with shrinkage and shrinkage cracking. And before we get into the depth of the module, we'd like to begin by talking a little bit about the learning objectives. First, what we'd like to do is we'd like to understand how shrinkage relates to stress development and how this stress development can lead to early age cracking in the concrete. We're going to try to understand the different types of shrinkage, and we're going to try to understand the causes behind them, what causes them, and how they can be mitigated. We want to understand a little bit about why lower water to cement ratio concretes may be prone to cracking. We're going to talk a little bit about how internal curing can help to reduce the potential for cracking. Then finally, what we're going to do is review some data that compares the cracking behavior of plain and internally cured concretes. So with these objectives in mind, let's begin. And we can begin by talking a little bit about why we are so worried about cracks in the concrete industry. Cracks are frequently observed. Here we can see some photos from bridge deck. Transverse cracking is observed in over 100,000 bridges according to NCHRP. Many DOTs consider cracking a problem. The reason is cracks can shorten service life, they can increase the maintenance cost, and they're going to accelerate corrosion, which has the potential to reduce the service life, impacting sustainability and then the life cycle costs associated with that part of the infrastructure. In addition, in many cases, cracks are unsightly, and what we're talking about here is not reducing all cracks or eliminating all cracks in concrete structures, just the cracks that can be avoided due to maybe thermal cracking or due to especially shrinkage and water-induced cracking in these systems. So what we want to do is we want to talk a little bit about where these cracks may come from. Where do these early age shrinkage and thermal cracks come from? And the basic idea here that we know is that concrete is going to reduce volume when it loses moisture or when there's a temperature reduction. So as water leaves the system, concrete is going to shrink and get smaller. If this volume reduction isn't restrained, the sample will just shrink and get smaller. So the concrete would just shrink, get smaller, and there really wouldn't be an impact. However, in many cases, the structure, the pavement, the slab, is prevented from shrinking freely from the surrounding elements, the things the slab is attached to, the friction, for example, with the ground. And when the concrete is restrained from shrinking the way that it wants to, tensile stresses can develop, and if these stresses get high enough, they can result in cracking. So here we can see a simple equation that tells us about the stresses that are developing, where the left-hand side of the equation tells us what's the strain that's being permitted. And if our structure is completely restrained, that would be a value of 0. And that's going to be equal to the incremental stress divided by the time-dependent modulus, plus the incremental shrinkage that we have in the system. So this is simply an application of Hooke's law. It says that the stress is going to be related to the amount of shrinkage that occurs as well as the elastic modulus inside of the material. Now, many concrete elements are restrained. This could include slabs on grade that would be restrained by subgrade, or items that penetrate the slab like columns or like walls that will come through the slab. Slabs on girders or beams are going to be restrained by their connection to the beams and the girders, and in many cases, to make the structure more efficient, we try to tie that beam to the girder to get composite action. Things like bonded overlays or topping slabs are going to be restrained by the substrate. The concrete is going to want to move around due to temperature and moisture changes, but the substrate will prevent that or restrain that from happening. Patching materials, for example, are going to be restrained by the material, the parent material that the patch is being placed on. Very high levels of restraint when we're looking at patching materials. And in many cases, it's really hard to remove this restraint in practice, so what we really want to try to do is to design our concrete so that it shrinks less, so that it will have less built-in stress overall in the system. Now, we talked a little bit about how we could estimate these stresses using Hooke's law, and here what we saw is that the permissible strain, the left-hand side of the equation, is equal to the incremental stress divided by the time-dependent modulus plus the incremental shrinkage. And if we do a calculation like this, we can see that the tensile stresses will develop substantially over time, and when these exceed the tensile strength of the concrete, we can think about a crack that would be forming. So once we start to exceed 5 or 6 MPa, once we start getting over 400, 500 psi, we could expect cracking to start to occur. However, and very fortunately for us, Hooke's law is a simplification of what happens in concrete, because in concrete we actually have what's referred to as an aging viscoelastic material. Now this viscoelasticity is important. This essentially allows the stresses to be relaxed out of the system. So if we pull on a system and we hold it at a constant deformation, over time, those stresses will actually be reduced. This is a lot like pulling a rubber band, leaving that rubber band over a longer period of time, and you'll realize that rubber band has sort of become stretched out. That stress relaxation in a rubber band, it has to do with the polymer chains essentially untangling. In concrete, this has to do with essentially the CSH sheets sliding over top of one another when there's water present inside of the system. So this stress relaxation is actually very beneficial in a restrained shrinkage problem, because what it's going to do is it's going to help to reduce the stresses that are inside of the system. So as we saw before, we had the initial specimen. The specimen underwent shrinkage. We restrained the shrinkage to build the stress back up in the system and to maintain that zero displacement. But under that sustained stress, under that constant displacement, we would see that creep or microcracking would actually be occurring in the sample, and that would essentially work to relieve the stresses in the system through this viscoelastic or creep or relaxation type of effect, and this would result in an overall lower state of stress in the system. Here you can see the types of relaxation that we're talking about: 50, 60, 70% of the stresses being relaxed out of the system. So there's really two important components that we can look at in this equation, that in addition to shrinkage, the other main players in how much stress develops in the system are going to be the elastic modulus and the viscoelastic component that we see in the system. The higher the elastic modulus, the higher the stress that's going to develop in the system. The lower the creep, the higher the stress is going to develop in the system. So if we want to try to reduce the potential for cracking, we're going to try to reduce the shrinkage. We would also want to increase creep, and we would want to reduce the stiffness of our concrete to help to keep these stresses down inside of our concrete. However, in determining whether cracking occurs, what we frequently notice is that it's not as simple as just figuring out when the stress inside of the system exceeds the strength, that being in the age of cracking. Typically, when we start to look at this and we start to wonder where this might become a problem in the field, we begin to start getting concerned if the stresses start to exceed about 70% of the tensile strength. And this is partially due to moisture gradients, it's partially due to probabilistic concerns, it's partially due to a phenomena called creep rupture. The basic idea here is that we really want to try to keep the stresses in the system as low as possible, but once we start to get to about 70% of the tensile strength, we really have to worry about these unwanted cracks starting to form, and starting to form very quickly inside of our concrete. Now, just to bring this back together, we can see the green line, which was what we were talking about earlier, which was the stresses that are developing just based on Hooke's law or elasticity. We see stress relaxation coming from the viscoelastic component, which reduces the stresses, that green line, to the blue line, which are the stresses that are actually developing in the system. And we can now start to compare that with the tensile strength or the resistance to cracking, which we see here in black. And when the strength starts to be exceeded by the stress that's developing inside the system, there we can start to worry about the potential for the crack to form in the system. Now, we can write this expression out and we can start to look at all the components, and as I was mentioning before, we're really starting to worry about the volume change or the shrinkage, the incremental shrinkage that occurs in the system. But there are several other parameters that come into the discussion of early age cracking. So later on, we're going to focus in on ways that we can reduce the shrinkage, and that's going to focus on reducing this incremental shrinkage term that we see in the middle of the equation. However, there are many other things that we can look at that are also going to increase or influence the potential for cracking. What we can see here is the elastic modulus plays a large role in this problem. With a higher elastic modulus, actually leading to higher stresses developing in the system. What we'll see in Module 4 is that internally cured concrete will actually result in a lower modulus. It'll enable the concrete to be stretched over a longer distance, developing lower stresses in the overall system, and therefore lower elastic modulus of the internally cured concrete is actually beneficial to help reducing the potential for cracking. So in addition to now shrinkage and the elastic modulus, we know that the degree of hydration is going to play a role here with the elastic modulus and the aging coming into the picture. All of a sudden, we're going to start to see things like the strength developing. We're going to see the elastic modulus developing in the system. So hydration plays a role. We're going to see that the viscoelastic term plays a very large role here, where the more moist the system is, the more viscoelasticity we can expect in the system, the more stresses that are going to be relaxed out of the system. And the degree of restraint is also going to play a role in this picture. So it's not simple, it's simply not enough to just look at the shrinkage, but we can see the shrinkage is a major component, coupled with the elastic modulus and coupled with the viscoelasticity to determine the potential for cracking that develops in the system. Now, many people will look at this stress versus strength curve, and they'll essentially be led to think that the real issue here is that the concrete doesn't have sufficient strength, and they'll start to look at ways to increase the strength of the concrete. We're going to look at ways to look at the strength, the volume change, the modulus, the viscoelasticity, look at many parameters to try to reduce the potential. So as I mentioned before, many people are going to look at ways to increase the strength of the concrete to make the concrete more resistant to cracking. So what you'll see people doing is moving to lower water to cement ratio mixtures. This will make the concrete stiffer. This will make the concrete have lower viscoelastic performance. And what they'll do is they'll increase the strength with the idea that, well, if we raise the strength high enough, we can get above the stresses that develop in the system, and we may not have cracking. And while this is an interesting approach, this may not really tell us the entire story, and we have to look at what increasing the strength does to all of the other properties that we've been previously talking about. As we increase the strength, we need to remember that we also increase the elastic modulus, and this is going to increase the built-in stresses. We're going to decrease the viscoelastic effect, so we're going to have less creep going on in the system. So frequently what ends up happening is by increasing the strength of the system, we increase the built-in stresses because of the higher modulus and the lower viscoelasticity, and we can actually shift the age of cracking to an earlier age when we went to a higher strength concrete. So we've tried to make the concrete stronger to resist cracking, and what we've ended up doing is making the concrete stiffer, less forgiving, less relaxing, and we've exacerbated this problem of cracking. And this is something we frequently see when people go to higher cement contents and they go to really high strength concretes, that we may be actually exacerbating the potential for cracking to occur in the system. So increasing the strength can frequently be outweighed by some of these other factors, and what we want to do is we want to look at other ways that we might be able to reduce the potential for cracking. So again, just to really bring this home, we want to look at shrinkage, but in addition, we can't look at this without looking at some of these other parameters: elastic modulus, strength or brittleness, toughness, and viscoelasticity in the overall system. So if we go back to the beginning and we start to look at really what's driving the shrinkage in the system, here we can see some data from Lee Hermite that basically examined the shrinkage of the concrete over time, shown in blue, being a combination of the shrinkage of the paste, which is shown in red, and the shrinkage in the aggregates, which is shown in green. And the real takeaway from this is that shrinkage is really a paste property. This means that it's really the water and the cement that are important, and it's the volume of the paste that's really going to drive how much shrinkage we get in our concrete. So one of the first things that we want to do to reduce shrinkage is to reduce the volume of our paste. Reduce the amount of cement plus water that's inside of the system, because in general our aggregates are volumetrically stable, but it's really the paste that's driving the overall shrinkage in the system. Now, when we start to think about this, it's commonly thought that by many people that having a lower water to cement ratio is the key to reducing shrinkage. And you'll see graphs that appear in the literature that look like this graph that we see in the upper left-hand side here that is shrinkage versus the water to cement ratio. However, I want to go back to this idea, as we've seen before, that shrinkage is really a paste property. And the first thing that we do to control shrinkage is to reduce the amount of paste that's inside of the system. In addition, we can actually argue that it's the smaller pores, and we'll see this argument later on, that really drive the shrinkage. And the gel pores that develop in these systems are going to be very similar irrespective of the water to cement ratio that we have. So where do we get this idea that the lower water to cement ratio concretes exhibit less shrinkage? Well, one of these is wrapped up in how we actually measure the shrinkage inside of the system. So the shrinkage measurements actually start at 24 hours typically if we're following an ASTM C157 type test. However, if we started to measure the shrinkage right after the time of setting, what we would notice is a very different trend that's shown here in red, where the lower water to cement ratios start to have much higher shrinkages taking place at very early ages. So now if we start to say, well, what is the shrinkage that's happening before the first 24 hours that we're missing in our conventional tests, which is shown here in red, plus the shrinkage that we would see after 24 hours, which is shown in blue, if we add those two together, what we're going to notice is that there's a very, very small impact of the water to cement ratio and the shrinkage that's taking place. So the real issue here, again, is not necessarily the water to cement ratio itself per se, it's the volume of paste that's in the system, and it's the way that we measure the shrinkage that really start to become important. So the key to controlling shrinkage is really controlling the amount of paste or the water content in the system. And this really points out that if we just measure using standard ASTM 157 types of approaches for higher performance concretes, we may be missing out on some of the shrinkage that's occurring in those systems. So in lower water to cement ratio concretes, why is it that this shrinkage is high at these early ages? And again, I want to point out here that sometimes time is really passed on the conventional line of reasoning or the conventional line of wisdom. And here we can start to examine why this is the case. And to do this, we're going to have to start to examine two different types of shrinkage that are taking place in the system. And what we want to do is build up the foundation on the different types of shrinkage that are taking place, the chemical shrinkage and the autogenous shrinkage, and we're going to just try to describe the background on each of these so we can really understand the role of internal curing in reducing the shrinkage of high performance concretes. Now, to understand the chemical shrinkage part of this, we really need to start out with Le Chatelier. And Le Chatelier's idea here was that if I take the volume of the cement and I add the volume of the water together and I say I take a certain volume of cement, I react it with a certain volume of water, I should seemingly get the volume of cement plus the volume of water. However, in reality, that's not the overall volume that I get at the end of the reaction. What Le Chatelier said was that the volume of the reactants was actually larger than the volume of the products. This difference is known as chemical shrinkage. So the idea here is when the atoms will rearrange themselves, when the compounds rearrange, when the reaction occurs, the overall structure of the material is smaller than the volume of the materials that you started out with. And this volume reduction is chemical shrinkage. Now, chemical shrinkage then is an indicator of how much reaction has happened. And chemical shrinkage occurs in every single cement that we're going to be looking at. We're going to see a chemical shrinkage, a volume reduction that's going to occur, and that's natural, that happens as a part of the hydration reaction. So when we look at chemical shrinkage, we can define chemical shrinkage simply as the volume reduction associated with the hydration of cementitious materials. We can look at Power's model and we can see that unhydrated cement and capillary water decreases. We hydrate more of the cement. We get more solid products forming. We get more gel products forming. But we also are getting this volume reduction that's forming in the system. This volume reduction becomes very important because it can be a measure of the overall hydration of the system, but it also starts to be a volume that we need to start accounting for as we start to move forward. Now, since chemical shrinkage is the volume reduction associated with hydration reactions, There are several different ways that you could look at this, and it could actually be based on the chemistry of your cement, and we can get into a lot of details on how this may be varying by a particular cement or from one cement to another. But Power's model showed about a 6.4% reduction in volume when you average this out over different cements. So when we're talking about an ordinary Portland cement, we'll see about a 6.4% reduction in volume when that cement has fully hydrated. When we start to talk about supplementary cementitious materials, the chemical shrinkage goes up. So a C fly ash or a slag, we may see this number going up as high as doubling. When we start to see other materials like silica fume or something like that, where we have the pozzolanic reaction, we can see this going up even higher to be 3 or 4 times the value of chemical shrinkage of Portland cement. Now, how do we measure this chemical shrinkage? How do we know what the total volume reduction is? There have been several methods that have been developed over the years, but there's a standard method called ASTM 1698, where you simply place a small volume of the hydrating cement paste in the bottom of a vial. You measure the amount of water that drops in a pipette, and that volume that drops is essentially the volume of chemical shrinkage that occurs, provided you can get water fully throughout that paste system. So in order to do that, we typically use a very small amount of paste, and we really make sure that this whole system, we've gotten rid of a lot of the air bubbles and things like that in the system, and we can measure this chemical shrinkage that's taking place over time. In addition, there are other ways that you could actually do this. Here we can see a technique that's based on buoyancy, where we can measure the chemical shrinkage as a function of time. The whole idea behind using this type of approach is that instead of looking at the vial, this is something that could be automated. And what I want to really try to point out is both of these methods will give you the same types of results. They will give you a very similar measure of the overall chemical shrinkage. But by being able to take these measurements continually, what you'll notice here is a chemical shrinkage curve as a function of time that has a rapid chemical shrinkage at the beginning. We start to see a slowing down period or a plateau period. Then all of a sudden, around 8 hours or so, we'll see a rapid increase in the chemical shrinkage taking place, and then that will start to slow down over time. It's important that we remember that chemical shrinkage is proportional to the amount of the reaction that's occurred. So this will look exactly like a heat release curve over time, or simply a measure of how much reaction is taking place as a function of time in that overall system. Now, we've talked about chemical shrinkage, and what we want to be really clear about now is when we're talking about chemical shrinkage, we're talking specifically about the total volume change of the cement due to the reaction. We're going to shift gears a little bit here, and we're going to talk about autogenous shrinkage or autogenous strain, and this is going to be a fraction of the chemical shrinkage that's occurring in the system. Autogenous shrinkage is defined as the bulk strain of a closed isothermal cementitious material not subjected to external forces. Now that's a lot, so what does that really mean? What we're saying is this is the external deformation of a body that's sealed. So while chemical shrinkage is the total volume change, the autogenous shrinkage is just the external volume change that we may measure on a particular concrete. Now, as I mentioned, the autogenous shrinkage is going to be a portion of the chemical shrinkage. So what is the remainder of the chemical shrinkage going to be made up of? Well, we know there's going to be a total volume reduction. However, after some point, the cement particles begin to impinge on one another, and the total external volume change can't be equal to the total volume change that's happening in the system. And what we will see is vapor-filled spaces starting to form inside of the matrix. These vapor-filled spaces, shown here in yellow, will give rise to this idea of self-desiccation happening in the system. Now, it's important to understand that this concept of vapor-filled spaces forming happens in every single concrete every single day, unless there's an infinite amount of water an amount of water that's being placed at the surface of the concrete. However, these vapor-filled spaces become very, very important in lower water-to-cement ratio systems, mainly because the size of the pores that these vapor-filled spaces can form in. If they form in large pores, generally they don't result in the development of a lot of stress. Therefore, you don't see a lot of external volume change. However, as these vapor-filled spaces start forming in smaller and smaller pores, we're going to start to see a higher capillary stress developing inside the fluid. That higher capillary stress is going to essentially put the fluid under a tension. It's going to pull in on the solid particles, and we're going to see an overall volume change, and that volume change that we're measuring is the autogenous shrinkage. So again, just to recap, chemical shrinkage is the total volume reduction due to the reaction, where autogenous shrinkage is just the external volume change. And the difference is really going to be vapor-filled spaces that are forming inside of our cement paste. Now, there are several different ways to measure autogenous shrinkage. You could measure this using a sealed prism like ASTM C157. The big question here is trying to start the test at the appropriate time, really starting it around the time of setting. There's an alternative test called the membrane test, where you essentially place a paste inside of a sealed membrane, and then you can essentially measure the volume change by suspending that in water. There's a rigid form where you can essentially measure length change using a non-contact laser. And what we'll see here is the corrugated tube test, which you can see in the upper right-hand corner. This tube looks sort of like a crinkle-cut French fry with a very high stiffness in the radial direction and a very low stiffness in the longitudinal direction. So a fresh mortar, paste, or concrete can be placed in a tube like this and can essentially be placed in the tube while it's fresh. The ends can be sealed off, and then you can measure the volume change inside of this tube. Now, the real meaning of this test really starts at about the time of set, and then you can measure the overall volume change as a function of time. And if you compare these tests and account for any of the differences or any of the inconsistencies that may happen with leaking or temperature changes or things like that, once you've accounted for all those things, what you'll notice is all four of these approaches can give us a very, very similar value. The benefit of the autogenous corrugated tube test is it happens to be a relatively simple and straightforward test to perform. This test has also been standardized by ASTM and provides good agreement with the other test methods that are out there. So if we really want to start to get back into this whole idea of chemical shrinkage and autogenous shrinkage and what's happening in the overall system, we need to remember essentially that we're looking at a system that is somehow transitioning from a fluid, becoming a solid, and it's really when this solid starts to form that we start to see differences in the overall system. So if we start out at the beginning, what we can see is we've mixed our water and our cement together, and as our cement starts to react, we start seeing this chemical shrinkage. This chemical shrinkage essentially starts to cause the system to want to shrink overall, and we want to start to measure the external volume change, and the external volume change is going to be exactly identical to the chemical shrinkage that's taking place in the system, because since it's a fluid, the system just keeps collapsing upon itself. So at our earliest ages, we can see that the chemical and the autogenous shrinkage are very, very compatible. It's at the time where the system starts to solidify. So once we start to go through setting or we start to go through solidification, all of a sudden the chemical shrinkage continues to take place because we're having reaction, but the overall volume change of the system really starts to slow down because the cement particles start to impinge on one another. They can't continue to just keep collapsing, and all of a sudden now we're going to start to build up a capillary pressure inside the system. We're going to start to build up this under pressure in the fluid, and we're going to start to create these vapor-filled spaces that we were talking about before. So all of a sudden these pockets of vapor are going to start to expand, and that's really what's going to give rise to this concept of self-desiccation. So before setting, the chemical shrinkage and autogenous shrinkage are very similar. After setting, however, what we're going to start to see is the chemical shrinkage continues to take off, but what we're left with is a concrete that's undergoing an autogenous shrinkage, a shrinkage that's occurring for a sealed concrete at a constant temperature. And the amount of shrinkage that takes place is really up to the amount of vapor-filled spaces that form and the size of the pores that those vapor-filled spaces form in. If they form in very big pores, we're not going to generate much capillary stress. However, if they start forming in smaller pores, this is where those stresses really start to rise. And here we can see an example, again, just to drive home this concept of the differences here between shrinkage in a sealed case, shrinkage when we have drying, and how this is all related back to pore sizes. If we have our sealed concrete, we're going to get these vapor-filled spaces forming inside the core of our concrete. When we have drying, we're really talking about a meniscus on the surface like we see in the middle. In an unsealed type of concrete, we have both of these cases going on where we've got the combination of autogenous shrinkage plus drying shrinkage leading to the overall total shrinkage that's happening inside of our system. The amount of shrinkage in our concrete is really going to be related through all of these factors that we see inside of the first equation, where we're going to start to see that the shrinkage of the concrete is equal to S, which is the saturation factor, gamma, which is the surface tension of the fluid, R, which is the pore size or the radius of the meniscus that's really emptying out, the size of the pores that are essentially emptying out of the system. The K values talk about the essentially the bulk modulus or the stiffness of the solid material and the structure that's forming, and then again the volume fraction of the aggregates or the amount of paste that's inside of the system. When we start to really look at the shrinkage of the concrete, we can see here that it's the saturation of the system, how much fluid is in the system, and really the size of the meniscus inside of the pores, the size of the meniscus in the pores that are emptying out, that really drive the overall shrinkage, all other things being equal. The real takeaway here is that with R being in the denominator, the smaller the pores are that are emptying out, the higher the shrinkage stress is going to be in the system. So in a higher water to cement ratio concrete, a 0.5, a 0.6 concrete, we can empty out fairly large pores and not generate a lot of shrinkage. As we get to a higher performance concrete, where we get to lower water to cement ratio materials, where we get to materials where we're using a lot of finely divided smaller powders, we're going to see this value of R really decrease, and that's going to drive the shrinkage up in the concrete. So those are really some of the important distinctions, and this is one of the reasons why shrinkage is a much bigger issue for higher performance concretes. So again, just to try to make sure that we're all on track with these definitions, drying shrinkage is the shrinkage specifically associated with the loss of water to the outside. This is going to result in pores of a specific size emptying out and a change in the relative humidity. Chemical shrinkage is the volume change associated with hydration reaction, and this is essentially the total volume change that's happening in the system. Autogenous shrinkage is just the volume reduction if we have a sealed system, not changing temperature, not absorbing or giving off moisture, not subjected to external forces, and autogenous shrinkage starts to go up in lower water to cement ratio, higher performance types of concretes. So we really need to make sure that we understand specifically what shrinkage is, what's the shrinkage that we're really talking about in these different systems. Now this can really start to lead us into where internal curing can start to play a role in improving the shrinkage and improving the cracking resistance of our concrete. So what is internal curing? Here if we look at the top, we can see the concept of external curing, where maybe the dark spots represent aggregates. And we can see that if we were to use conventional curing methods, where we may supply additional water from the outside, we're somewhat dependent on how far that water can penetrate into the concrete to the vapor-filled spaces that could be filled back in that overall concrete. Now, in a high water to cement ratio concrete, this water penetration depth can be quite large. However, as we reduce the water to cement ratio of our concrete, as we use materials with a more fine ground, more finely ground cement, smaller particles, nanoparticles, silica fume, what we're going to notice is we're going to densify that concrete. That's one of the main reasons why we're using those materials. The more dense we make that concrete, the harder it's going to be for that external water to penetrate and fill in those vapor-filled spaces that are forming in the center of the concrete. The idea behind internal curing is shown on the bottom, where the concept here is actually quite simple. What we're going to do is we're going to replace some of the aggregates, some of our normal sand aggregates that are inside of the system, with these green and white filled inclusions. Those filled inclusions are essentially going to be the lightweight aggregate that we're talking about. They're going to contain water, and as the paste needs that water, as this under pressure starts to develop, water is going to be drawn out of the bigger pores in the lightweight aggregate and is going to start to work its way into the paste. And the goal here is really to do two things. One, it's to supply enough aggregate that you have enough water that it can essentially handle the demand that's going to be created by the hydrating cement. So you'll hear us talk about putting in enough water to compensate for the volume of the chemical shrinkage. What we want to do is provide enough water that can fill in all that vapor-filled space. In addition, what we want to try to do is get enough aggregate into the system that we get them closely enough spaced that these particles are so close to each other that we can get water from the aggregate into the paste. So typically what we want to try to do is have the particles spaced about every 2 millimeters. We want to have a ring of paste that's protected by each one of those aggregates. So the whole concept of internal curing we can see is defined by ACI in 2011 as supplying water throughout a freshly placed cementitious matrix using wet reservoirs. This is the pre-wetted lightweight aggregate that we're talking about. This pre-wetted lightweight aggregate will readily release that water as it's needed for hydration to replace the moisture lost through evaporation or self-desiccation. What we're really saying here with self-desiccation is we're hiding water in the lightweight aggregate. That water is going to come out and it's going to fill in the vapor-filled space. So by hiding water in the lightweight aggregate, that water is going to come out, it's going to fill in the vapor-filled space, it's going to increase the hydration of the cement, of the supplementary cementitious materials. By doing that, it's going to increase the strength of our concrete, it's going to reduce the transport properties of our concrete, and what we're specifically talking about in this module is it's going to reduce the shrinkage and reduce the shrinkage-induced cracking that occurs inside of these materials. So the whole idea here is to use pre-wetted lightweight aggregate that will supply water at the right time to fill in the vapor-filled space that's caused by chemical shrinkage. And by doing this, we're going to improve hydration, we're going to reduce shrinkage, and we're going to cure our concrete from the inside out. So why is it that the internal curing works, and why is it that internal curing works with lightweight aggregate? As we can see on the upper right-hand corner, the way that lightweight aggregate is made is it's made essentially by expanding these lightweight materials, by puffing them up, by putting vapor-filled space inside of those. If we pre-wet these, water will go into those vapor-filled spaces, and the key issue here is that the pores in the lightweight aggregate are slightly bigger than the pores that are inside of the paste. So if we look at our left-hand side on the bottom, we have a pore size distribution, an example of a pore size distribution in paste, or an illustration of this. The biggest pore is empty first. So if we can place something that has water inside of it with bigger pores, water will preferentially leave the lightweight aggregate and keep the paste filled. The interesting part about this is that the water comes out of the lightweight aggregate at exactly the right time. Before the concrete sets, there's really not a pressure developing inside of the paste. There's really not a need for water to come out of the lightweight aggregate because the system can keep collapsing upon itself and we're not really creating a lot of vapor-filled spaces or under pressure that needs to be dealt with. However, after setting, once we've locked in the microstructure of our concrete, now all of a sudden we can supply water that's only going to help to reduce shrinkage and increase the hydration. And this is like a trigger that says, okay, let's start taking water out of the lightweight aggregate and let's start internally curing our concrete. So how do we determine how much water we're going to have in the system? We essentially are looking at placing enough internal curing water to fill in the volume that's created by chemical shrinkage. As we mentioned earlier, we can measure the chemical shrinkage either using the ASTM test, where you essentially have a small vial with a pipette on the top and you can measure the volume change, or we could use the buoyant technique, where we're essentially measuring a mass over time and converting that over. But what you'll notice here is The area shown in yellow is essentially the difference between the chemical and autogenous shrinkage. That's the vapor-filled space that's going to be forming. And really what we're trying to do is we're trying to do a simple calculation that says, what's the volume of the chemical shrinkage that's occurring? That's the volume of water that I want to supply inside of the lightweight aggregate. So the desire here is to really try to keep the pores filled with water. And we'll see two examples here where if we placed water on top of our concrete and we did water types of curing, we did a water immersed curing, what we would see is that the water could be drawn into the pore structure and not allowing this vapor-filled space to form. So on our left-hand side, we see a ponded system. As that chemical shrinkage would start occurring and as we would start to want to form those vapor-filled spaces, water would just be drawn in or pulled from the external surface and fill in those spaces. However, in many other cases, we don't do water curing and we essentially use a condition that's close to sealed. We may just put a layer of plastic on top of the surface, or we may go through and use a curing compound or something like that on top of the surface. This is different than water curing. Essentially, in this case, what we're doing is we're minimizing the evaporation that can occur, but we're still going to see these vapor-filled spaces. And in our right-hand image, those vapor-filled spaces are essentially the yellow spots that are forming inside of the system, where the aqua is essentially the original water, and the grays are essentially the cement particle, and the darker gray is the hydration products that are forming. So the real difference here is with external water curing, we're going to draw water in or suck water in from the outside, but in the sealed case, we're going to have the system undergoing some self-desiccation where vapor-filled spaces are forming inside of the concrete. Now you may say all this sounds like something I don't see in my normal concrete, but I want to take this step back and I want to say that this happens every single day inside of concrete. Many people notice or they see that bleed water can come to the surface of concrete. Well, actually what's happening is all the other particles are sinking down, and it's really kind of the water that's not sinking as fast as everything else, and that's forming the sheen on the top surface. Now the interesting part of this is we know that when the water sheen goes away, this is really correlated to the time that the concrete starts to set. In other words, this is really correlated to the time that an underpressure starts developing in the fluid that pulls this additional water away from the surface to make sure that we're minimizing the vapor-filled spaces that are forming inside of our concrete. So once our concrete sets, water gets reabsorbed back into that concrete, reducing this underpressure that's forming inside of the system. So this concept happens every single day. The difference here is instead of talking about the bleed water or placing additional water on the surface, we're going to have pockets of water inside of the lightweight aggregate that's spread out throughout the concrete that will now be pulled out of the lightweight aggregate the same way that that bleed water was being pulled back off of the concrete surface. So the water will stay in the lightweight aggregate until the capillary pressure starts to develop. So here we can see some cement particles shown in gray, we can see some pore solution shown in blue, and we can see a bigger pore in the lightweight aggregate. As the system starts to hydrate, and if this system is sealed, we could expect a pressure or an underpressure to be forming, and if this was just sealed, we would essentially be creating vapor-filled spaces. However, if we have this pre-wetted lightweight aggregate in the system, what we're going to do is we're going to preferentially draw the water out of the lightweight aggregate. As that water is drawn out of the lightweight aggregate, it's going to keep the paste saturated, it's going to keep the paste full of moisture, and it's going to be hydrating more of that system, and it's going to be reducing the overall shrinkage that's taking place in that system. So as we go through, we'll see a series of different calculations, but the whole idea of how much water do we supply to the system, that's based on this simple formula here, that it's going to be the amount of cement that's in the system multiplied by the volume of the chemical shrinkage that's going to occur times how much of the cement is going to be reacted, or the degree of hydration. So here, when we calculate how much internal curing water we're going to need, it's really just to replace the volume of chemical shrinkage, the volume of these vapor-filled pores that are going to form, and it can be calculated with this simple equation. Now, while this equation allows us to calculate the volume of water that we need, there are two other factors that we need to consider when we start to look at the internal curing and the lightweight aggregates that are being used. So you may recall in Module 2 we discussed something called the desorption behavior. The basic idea here is we want the lightweight aggregate not only to be able to store water, but we want it to be able to desorb, or we want it to be able to give up that water easily. In other words, we want it to make sure that the pores that we're talking about are larger than the pores in the paste, so that water can come out of the lightweight aggregate and backfill the pores that are being emptied inside of the paste. In addition, as we've mentioned a few times here, we want to make sure that the water can come out of the lightweight aggregate, and we know that that water is only going to be able to travel a certain distance. That water is going to be able to travel typically about 2 millimeters or so. Here you can see sort of a dyed water that's coming out of a lightweight aggregate that's moving about 1 millimeter. So we want to make sure that the aggregates are well spaced. This is one of the reasons why we're going to use fine lightweight aggregate, or we're going to use sand, because we're going to get a lot more particles distributed throughout the system, and we're going to have a much better spacing. And we want to make sure that the water can be given up easily, or the water can be desorbed out of the lightweight aggregates. So now here we can start to get into some of the measures of these shrinkages. Here we can see some measured autogenous shrinkage for concretes. We can see the red showing a plain concrete. We can see the blue showing an internally cured concrete. Here we see the shrinkage of the 0.3 water to cement ratio plain concrete, where we're measuring about 120, 130 microstrain after 120 hours, where the internally cured concrete doesn't actually shrink, it shows a slight expansion, much the same way you would see an expansion if you just placed a concrete sample in a water bath, because all of a sudden we're going to be able to absorb more water, we're going to start to fill in those pores, and we're going to see a slight expansion in the overall system. So again, the takeaway here is plain concretes, we're seeing autogenous shrinkage. That autogenous shrinkage is going to be much smaller, or may actually be a slight expansion when we talk about internally cured concretes. Now, again, the whole idea here is when we use a different amount of lightweight aggregate, we would expect to have a different amount of shrinkage taking place in the system, because we're supplying a different portion of the internal curing water. So here what you can actually see is a study where the blue is essentially the shrinkage of a paste, the plain paste, and each one of these additional lines is going to be a certain amount of lightweight aggregate that's placed inside of the system. Now this value of 25.3%, the value shown in black, is really this volume of aggregate that really is matched up to the volume of chemical shrinkage, vapor-filled space that you would have inside of the system. And what we can see is when we replace only a portion of this, when we supply enough water to replace a fraction of the internal curing water, we'll see a slight reduction in the shrinkage, or a delay in a reduction in the shrinkage, maybe the 11% shown in red or the 14% shown in orange. When we get to the internal curing being supplied where we have enough water in the lightweight aggregate that it matches the chemical shrinkage volume, we see that slight expansion early on, and then we see a relatively flat behavior over time. And if we add in additional internal curing water, we're not going to see any additional improvements after that particular time. The takeaway, though, plain concrete, autogenous shrinkage, no drying taking place, but just shrinkage taking place because of these vapor-filled spaces that are forming due to chemical shrinkage resulting in self-desiccation. Adding internal curing water has benefits. If we make sure that we add the right amount of internal curing water, we'll see a slight expansion and then essentially no shrinkage as long as the concrete stays sealed. And here's just a little bit of a graph that essentially shows these different amounts of lightweight aggregate that would have been placed in the system, and where we'd really start to see that lightweight aggregate being depleted of all the moisture that would have been in it. So if we look at the 11% case, for example, around a day and a quarter, we really see that that aggregate has really run out of water that it can supply back and fill in the vapor-filled spaces. And if we look over here, after about a day and a half, in the 11% case, the red case that we see here, all of a sudden we start to see that shrinkage picking up. So the basic idea here is we want to supply enough water inside of the lightweight aggregate that we match that chemical shrinkage volume and that we essentially have enough water that will be in the system for the right amount of time. The other thing that we can start to do is we can actually measure the relative humidity that's inside of the system, and this is sort of an indirect measure of the size of the pores that are emptying out. And what you can notice here is that as we go from our plain system, again shown in blue, up to our correct amount of internal curing water to match the chemical shrinkage shown in black, or even slightly higher amounts, what we can notice here is that by supplying that additional water, we keep more of the pores filled up with water. Therefore, we empty out fewer and fewer pores, and we can keep the relative humidity inside of our concrete higher. By keeping the relative humidity higher, we have less shrinkage that's taking place in the system. We're also able to react more of the overall cement. So the equation that we see on the top, that's essentially the size of the meniscus, or effectively the size of the pores that are being emptied out. We can see that that's being directly related to the relative humidity. So as we supply more internal curing water, we keep the relative humidity of our concrete higher. Now, while measuring the volume, the shrinkage is very important, we also want to measure the potential for cracking. And one of the ways that this is done is by using something called the restrained ring test. So here we can see the restrained ring test, and the basic idea of this test is relatively simple. We can see the black ring, which is essentially a piece of steel, or in some cases this will be a piece of Invar. The yellow represents strain gauges that are mounted on that steel, and the gray represents concrete that's placed around that steel ring. The idea here is the concrete wants to shrink and get smaller. If the concrete didn't have the steel inside, the concrete would simply shrink. The steel will restrain that shrinkage from taking place. That steel will prevent the concrete from moving the way that it wants to move, much like the subgrade or the beam that the concrete is restrained by, or the parent material that a patch is placed into will restrain the concrete from moving. As that restrains, the steel is being pushed on by the concrete's being pushed on back by the steel. Stresses start to develop in the steel, and we can measure those steel strains that are shown here in the blue. And after a certain period of time, we'll all of a sudden see a drop in the strains that are measured inside of the steel. Now, that drop in the strain that's measured in the steel corresponds to cracking. But the whole idea behind this test is we could actually pretend that this concrete didn't even exist, put an artificial pressure on the ring, determine what that had to be to get the strains that we measured, and then turn the problem back around and say, well, whatever pressure we had to push on the steel to get the strains inside of the strain gauges, we can apply an equal and opposite pressure to the concrete and measure the stresses that develop inside of the concrete. So in the green box, what we can see here is the stresses that develop at the inside edge of our concrete, and the stress that develops in the concrete is going to be equal to the strain that we measure in the steel times the modulus of the steel, ES, times factors that are related to the geometry, ROS, the outside of the steel, RIS is the inside of the steel, ROC is the outside radius of the concrete, RIC is the inside radius of the concrete. So now we have a way to measure the strain in the steel. By knowing the modulus of the steel and knowing the geometry, we can convert that right over into a stress that's developing inside of the concrete. And here we can see the strain that's being measured, and as I mentioned, this could be converted over into a stress for concretes with different levels of internal curing. Again, the blue is no internal curing, and we can see the strain developing in the steel ring until an age of about 6 days, at which time the concrete cracks. If we provide internal curing water that's equal to the volume of chemical shrinkage that takes place, we get that black line where we see that there's virtually no strain developing inside of the steel ring, no strain developing in the ring, no stress developing in the ring, very low potential for cracking to be forming in the overall ring as we would expect. Now, if we start to plot out the amount of lightweight aggregate, what we can see here is the age of cracking really starts to increase with the more lightweight aggregate that we're using. And in fact, when we get to about 20% and 25%, we see no cracking taking place. So at lower levels of lightweight aggregate, we see that we can delay the time of cracking. At higher levels, we'll notice that we can essentially prevent cracking from occurring inside of those systems. If we also add in unsealed cases where we're adding in drying as well, we would expect that we would essentially empty out pores of the same size. So in a sealed case, what we're doing is we're essentially keeping the pores more filled. In the drying case, eventually we're going to come to equilibrium with the outside where we've emptied out the same volume of pores, and we may expect to have the same overall shrinkage at very long terms. But there's a big benefit in the unsealed case by keeping water inside of the system for a longer and longer period of time, because that can have the shrinkage taking place over a slower time, allowing us to get the beneficial effects of the lower stiffness of the concrete as well as the viscoelasticity that we see taking place in our concrete. So in the unsealed case, we're going to notice that the ages of cracking are faster than they would be in the sealed cases. And what we can see here, though, is we're going to start to see some benefits of having slightly higher amounts of lightweight aggregate in those cases, even higher than what we would have if we just replaced all the volume of the chemical shrinkage water. If we plot this in the same type of a way that we did with the sealed cases that were shown in red, in blue what we'll notice here is, again, as we start to add more and more lightweight aggregate, we can start to see the trend where we're reducing the potential for cracking at early ages. We're cracking at later and later ages, and once we get to a certain percentage of lightweight aggregate, we can see that we're not seeing cracking anymore occurring, and we're essentially getting to a vertical asymptote at around 30 or 35%. The whole idea here, though, is unsealed samples are going to require a higher amount of lightweight aggregate than what we would have calculated just by replacing the chemical shrinkage water, because now we have to deal with not only the chemical shrinkage vapor-filled spaces that are forming, but also the loss of water to the outside through evaporation. In addition, we can start to see some benefits of internal curing when we start to look at thermal cracking. Here we can see a dual ring test. This is very similar to the test that I just described, but in this test, instead of using steel, we're going to use Invar rings. The whole idea is that they'll have a lower coefficient of thermal expansion, so the restraint will essentially stay inside of the system whether we increase or decrease the temperature. And what we can notice here is a comparison between a plain system shown on the left and an internally cured system shown on the right. Now the x-axis here is the time, the y-axis is the stress or the temperature, stress shown in black, temperature shown in red. And what we can notice here is that in the plain system, we're going to build in a stress into the system where after about 12 hours, we're going to see the stress start to rise inside of the system due to this self-desiccation that we've been talking about. In the internally cured concrete system, you'll notice that that black line stays much, much lower for the first 3 days. This is because the internal curing is supplying additional water, helping to minimize the amount of shrinkage that's taking place. If we start to look after about 3 days, what we'll notice is that we've dropped the temperature of the system, and all of a sudden now the stresses start to rise. And this isn't very surprising. If we cool the system, we would have a thermal contraction. Thermal contraction would be expected to have stresses being developed inside of the system. The interesting part about this is this type of a temperature drop leading to stresses in the system could be very similar to what you might see, for example, if formwork is removed, or if all of a sudden we have some cooling at nights on our construction operation. The big difference here between the plain system on the left and the internally cured system on the right is in the plain system we had about a 10 degrees Celsius temperature change before the concrete cracked. On the right-hand side, same conditions. What we notice is that it took about 27 degrees of temperature change to get cracking in the internally cured mortar. Now, again, both systems cracked, but it took a much bigger thermal swing for the internally cured concrete to crack, and the main reason is we've reduced the built-in stresses that have come along with self-desiccation in this system. It's made our concrete more robust, more resistant to thermal cracking. We can track this out over different times. Again, same set of mortars, and what we notice is we have a bigger capacity or a bigger safety factor on our right-hand concrete where we're using the internal curing because we're reducing those shrinkage stresses that are developing inside of the system. Similar studies have been done at Auburn University under the direction of Anton Schindler, where people have been using, where he was using a control concrete, and then he was using internally cured concretes that might be used on a bridge deck, where these were sand lightweight aggregates or coarse lightweight aggregates or internally cured concretes. The main idea of this test is instead of using the ring, this is a linear sample, as you can see, sort of a dog bone shape, where the frame restrains the concrete from shrinking, much like your girder does, and you can measure the stresses that are developing in the system. In this particular case, what they did was they used 4 different cases where they were using different lightweight aggregates, and when they're talking about their internally cured concrete, they're not replacing the full chemical shrinkage volume. They're essentially designing their concrete to have a density of about 135 pounds per cubic foot. What we can see here is they were going through a case where they were essentially starting to talk about what happens when you are casting a bridge deck and when you're having the daily thermal cycles for a fall type of construction environment. And here what you can see is the plain concrete shown in black, the internally cured concrete shown in the bluish color. What you can notice here is a later date of cracking inside of the system. The main reason here is because you're reducing some of the stresses that are developing in the system. If you're using an all lightweight concrete or a sand lightweight concrete, you can see the orange and the purple curves respectively that are again reducing more and more of the stress that's inside of the system. Again, it's important to note here that this internally cured concrete doesn't contain the full volume of water that would be needed to essentially replace all of the vapor-filled space caused by chemical shrinkage. And you can see here that this was done for many different types of aggregates, aggregates that were made by expanding clays, shales, and slates, and in all cases the internally cured concrete delays the age of cracking. Similarly, this has been done in full-scale applications. This is a bridge deck from about 2010 that was done in Bloomington, Indiana. After 18 months, the plain concrete had 3 large cracks. The internally cured deck, no cracking was being observed in this system. The main reason, the lightweight aggregate is supplying moisture, reducing the shrinkage that's occurring in the system. 2012, some decks were placed in Utah. Spencer Guthrie and his group had looked at these. There were 2 bridge decks made with internal curing and 2 plain concretes, and as reported in 2013 at the annual TRB meeting, the internally cured concretes had 23 times less crack length than the plain concretes, and the main cracks that were noticed were cracks that had formed where there was a cold joint in the bridge deck while it was being constructed. Again, the main idea here is that you're reducing the shrinkage in the system, reducing the potential for cracking that's actually forming. In addition to just hardened shrinkage, what we're going to notice is internal curing can also be used to reduce plastic shrinkage cracking that happens. This is cracks that happen during the first 6 hours due to either autogenous shrinkage, settlement type shrinkage, or evaporation. Here you can see settlement sort of shown in circled in red, where you're typically going to see the concrete settling down due to gravity, usually where there's a difference in cross-sectional height, like in the pan joist system there, or over top of a rebar, you may see cracking. Green here we see a high rate of evaporation taking place, but autogenous will also come into this picture. Again, the idea behind this type of cracking is bleed water will essentially make its way to cover the surface. It'll be exuded from the concrete pushing down. If the evaporation rate is too high, essentially if the evaporation rate starts to exceed the bleed rate, we start to worry about stresses developing inside of the system. So where does internal curing come into play in this system? Well, internal curing really comes into the system if we compare the top system, which is a plain system, and the bottom one, which is the internally cured system. In the top system, what we'll notice is that we have a system where the cement particles tend to be fairly randomly spaced. As we start to settle, we'll notice that they start to consolidate. Water will come down in the system and we'll start to essentially consolidate. We'll have essentially a compression or consolidation of the cement particles. At some point they can't consolidate any further and a pressure is going to start to form inside of the fluid. When that pressure becomes too high, we'll essentially see a stress start forming that leads to a plastic shrinkage crack. On the bottom, we see a system where internal curing is used, shown as a water-filled lightweight aggregate as the red dot with the green center, which is the water from the lightweight aggregate. And as the system consolidates, water can come out of the lightweight aggregate, relieving this pressure and essentially providing more water that's available inside of the system. Until you started to evaporate, or until you started to pull all the water out of the lightweight aggregate, you don't really reach that falling rate period where the stresses would be high and would start to cause the potential for cracking. So the whole idea here is you could use that water at very early ages. And this was shown by Henkensifken, where we see here the blue being the plain system and increasing amounts of lightweight aggregate being red, pinkish, and the black color, to show that as we increase the amount of internal curing water, we can essentially greatly reduce or prevent plastic shrinkage from occurring. It's very, very important to note here, though, that if we're going to use the lightweight aggregate to help in the plastic shrinkage environment, that water is going to get used up and it's not going to be available for many of the other benefits that we're talking about, either in long-term shrinkage or increased hydration or other things that we'll talk about in Module 4. So if we can take a second to review, what we really want to talk about here is we really want to review the main things that we've seen in Module 3, which was focused on shrinkage and shrinkage cracking. The idea here is that concrete can be susceptible to cracking, and it's susceptible to cracking when it's restrained from shrinking freely. The cracking potential can increase with lower water to cement ratio, higher strength concretes. The main reason for this is because we're going to have more autogenous shrinkage taking place in these cases. We frequently see a rise in the cementitious content, which can be a rise in paste, and we can also see many times the pore structure being modified to have a smaller particle size distribution. And this really leads to that rise in autogenous shrinkage. Chemical shrinkage occurs as the cement hydrates. Chemical shrinkage is the total volume change. The external portion of this is known as autogenous shrinkage. Internal curing will reduce the self-desiccation by filling in the vapor-filled spaces that form. The lightweight aggregate will hide the water. That water will leave the lightweight aggregate, fill in the vapor-filled spaces, reducing self-desiccation and in turn reducing autogenous shrinkage. Therefore, internal curing reduces shrinkage and shrinkage cracking. Now, it's important that we remember that not only is shrinkage an important parameter, but the elastic modulus, the viscoelasticity, and rate will all influence the potential for cracking. So while it's important to reduce shrinkage, we also get benefits by having a more viscoelastic response in the internally cured concrete and a lower elastic modulus because more stresses can be relaxed out of the system. We also know that it's very important to talk about the different types of shrinkage that can take place inside of the system. Chemical shrinkage will simply be a volume reduction that occurs because of the chemical reaction between water and cement. Chemical shrinkage occurs as the cement reacts and as the cement hydrates. Autogenous shrinkage is a portion of the chemical shrinkage. It's really driven by this vapor-filled space that forms, resulting in self-desiccation, and it's driven by the chemical shrinkage that's taking place in the system. Autogenous shrinkage can be mitigated by supplying water in the lightweight aggregates. They will reduce the amount of vapor-filled space that forms. Therefore, they're going to reduce the capillary pressure and reduce the autogenous shrinkage. Drying shrinkage starts to describe water that's lost to the environment. When we use internal curing, we can slow down the rate of drying shrinkage, but at some point we probably get to having a very similar amount of drying shrinkage when we go long term. It's important to remember that as the water to cement ratio decreases, we frequently think the shrinkage decreases, but this isn't a complete picture because of when we start the measurements and how we do the measurements. As the water to cement ratio decreases, the autogenous shrinkage tends to go up, the stiffness of the system goes up, which leads to more stress, and the viscoelastic or creep components are not as prevalent, and they are going to lead to a lower amount of relaxation and more stress developing inside of our concrete. The internally cured water or mixtures are going to hide water in the lightweight aggregate. This water is going to be released after setting. It's going to help to fill in the vapor-filled spaces. It's going to help to saturate some of those pores. And the more filled in those pores are, the bigger the pores that are filled are going to be, the larger the meniscus is going to be, and the shrinkage is going to be smaller. This means that internally cured concrete is going to have less shrinkage, and it's going to be less susceptible to restrained shrinkage cracking than plain concrete. Finally, we also saw that internal curing can be used in fresh concretes to reduce plastic shrinkage cracking, so water can come out to help to mitigate the stresses that are forming there. But it's important to remember that in those cases, that water that's been used up for evaporation won't be available for later ages to help hydrate more of the system or to help in the restrained shrinkage cracking problem. With that, I would like to thank you for your attentiveness during Module 3, and I'd like to welcome you to email any questions that you may have. Thank you.